Well, videos 26 and 27 dealt with the subject of transient dynamics in a composite material when used when Catia's native solver is used to simulate it. Now, this video 27, 28, and 29 are dealing with a situation where this uh, response was not a function of t. In other words, the excitation that is used to simulate this response is not provided as a function of t. For, for example, a fan that is turning at a certain RPM, sitting on a composite plate, we don't really have to say what the excitation is as a function of time. We need to specify it, or we can specify it as a function of the RPM of the fan turning. Okay. Now, let me go ahead and get this thing into the slide mode so that we can discuss it better. Situation like that where the force or the excitation is not inputted as a function of time, but instead it's inputted as a function of RPM, or let's be more accurate, as a function of frequency, is called a uh, uh, harmonic response of a composite. Okay. Now, this also comes under other names, for example, frequency response, sinusoidal response, steady state dynamics, etc. The one that I'm going to be doing currently is a geometry, a rectangular, let's say, or a rectangular plate made of a symmetric laminate like that. Okay, and I'm assuming that the magnitude of the force which is applied is a constant as a function of the frequency of the input. And that is not a fan, for example. A fan, the magnitude of that force, if it's placed right there, is actually not a constant as a function of frequency, because it varies as a function of frequency. And we will get to that in the next video clip, not in this one though. Okay, so you have seen this geometry. This was done earlier in one of the videos, and uh, so let's see now. The details are given here. The information is given here. The only thing that I did not give you before was the density, because the problem that I did for you for this particular uh, geometry was, I believe, when it was a static load. Okay. So we are assuming that the concentrated force in the middle applied to that middle node center location is uh, given by this forcing function, but this F naught is independent of the frequency. And I'm going to be investigating the magnitude of the displacement of the center node, for example, in that frequency range. Okay, so but this is not a fan. Okay, a fan, you know that if there is an imbalance in it, the magnitude of that force is going to be the size of the imbalance, let's say m, times the distance that we can locate that position, that imbalance, mr, and then it's going to be times omega squared, the centrifugal force, basically. So we're not dealing with a fan. That's going to be appearing in the next video segment. All right, so let's go ahead and make this thing. Let's go ahead and make this. Close that. All right. We go to Katia. The first thing we're going to do is create our material file. So we go to start, mechanical, infrastructure, material library. And there is a name, double click on it. There's a new one that I'm creating. The name of it, I'm going to call the white noise frequency response. response. Okay. Under composite, the size of each layer is unidirectional, and the height of each layer is, or pi, is 1.25 0.125 centimeters, okay, which is what I have here, okay, four of them, 1 millimeter and 21 and 1.25 millimeter, okay. Okay, and then under analysis, it's 2D orthotropic, and I input those numbers. It was 1.48, E1 was 1.48, e to the 11, yes. E2 is 1.05, 1.05, e to the 10. The Poisson ratio in that particular problem, the data that I took was 0.3. Shear modulus 5.61 e to the 9, 5.61 e to the 9, and the same thing with the other one, with the other direction, 5.61 e to the 9. In that other plane, the data gives me, same thing, 5.61 e to the 9. Okay, so it has shear modulus, same shear modulus in all three. Now, this is a dynamic problem, therefore I'm going to need the density, 1800 kilogram per meter cube. So apply. I think we got everything that we need, and we say okay. And then let me check this thing, make sure that everything is there. Okay, very good. And then we're gonna save it in that folder, desktop. I think I called this thing harmonic response right there, and I'll call it harmonic response. Harmonic response. We're going to be using the same data, by the way, in the next video segment too. White noise. Well, I'll just call it harmonic response. Okay. All right. And yeah. And we close this. Now we're going to go to. Now we're going to go to our CATIA. Create that part file. And we'll call it harmonic response. White noise. Okay, so on a convenient plane, on that horizontal plane, we'll sketch a rectangle or a square which is 50 centimeter by 50 centimeter. Those are the dimensions of my plate. Okay, so this is 50 centimeter here, and by 50 centimeters it's there. Exit, fill it, F-I-L-L, fill that, join it. Okay. Let me create an access system. This is going to be used as my rosette. So I click on the access system and right click noise. Create a point and minus 20 for Y, so that moves the access system off that plane. See, it's right now the access system that I created is in that corner. So it's going to move it there so I can see my screen better, and uncheck the box, the current box. Now, save this thing, file, save management, save as. This is the name. Okay, very good. Okay, Now, a couple of things. I will create a point right at the center, of this plate. Okay. You might say, why do you need a point? Because, well, first of all, if I mesh this thing with the usual quadrilateral elements that I want, uh, I don't I don't have a feature to place the load at, at a location here, because it creates nodes for me. That's true, and elements, but I cannot place a load or something along that line uh, on that feature. Okay, so uh, let me create a point here. So the coordinates is going to be 0.25, x 0.25, y 0.25, 0.25, that point. Okay. Uh, so we say okay. Now notice that there's a little x here. There's a point here. Okay. Now we are going to save this. We're going to go to our composite design and create our parameters. Material, I just created it. We're going to go and retrieve that database. Desktop was called Harmonic Response. This was the material database that I created. We say OK. It's created right there. And then the rosette, add a rosette. This is the rosette that I want. You say OK. And if you don't want this thing, directions are plus or minus 45 degrees, which are already default things in the direction, so I don't have to do anything. And we say OK. And if you don't want this thing, we can hide. I'll leave it like that. That's fine. Okay. Then we're going to create our plies, 4 of them. So I'll do 2, and then I use symmetry to reflect it down below. Okay. So we create a ply group. This is a surface. Draping direction is up, and yep. So we say OK and lock the ply draping directions. Okay. So there we are. This is group 1. And then we create our first ply, which is my first ply is going to be this one on the top. Okay, plus 45 degrees, so I do plus 45. This is the second one, and then we move on. So let's go here. All right, so first ply belonging to that plies group, the boundary is that sketch. Okay, and it is plus 45 degrees. Okay, fine. Then the next one in the same plies group, same boundary, is going to be minus 45. Okay, and we can check it. So let's check it out. Ply exploder, apply. So the first ply on the top, which is well, or this red one, first ply was the red one. Okay, and then the second one, fine. And now we're going to instead of doing the next 2, we're going to use the symmetry. So the plies group is right here, and it's non-pivot. Non-pivot means create 4, basically reflect both of these with respect to that, and that's what I want. And now we look at the ply exploder, apply. So you can see that we have 45, minus 45, minus 45, and 45. That's what I want. Okay, good. So save everything. All right. Now we're going to go to advanced meshing tools. Uh, we're going to create a static problem. Our problem is dynamic, but the way I explained it in the previous 2 videos, we do static, we do extracting, we extract the frequencies, and then we're going to do the transient, either transient dynamic or transient harmonic, okay? Harmonic transient. Okay, good. Now, in the past, what I did was use this advanced meshing to this advanced surface measure. All the problems that we have done so far involved this one. I never used this guy, but there are certain things that you can do in here that you will not be allowed to use in the surface measure. In the surface measure, there is no way I can make sure that this point is included in my node. So here's what I'm going to do. I'm going to go, please realize that this is a brand new thing that we are doing. Okay, advanced surface measure. It allows you to pick this. Okay, and the normal. Just remember the normal to this elements are going to be down, which is okay. There's no problem. Okay. Now we say that I want. Let's see now. Let's say I want. This was 50, right? This was 50 millimeters. So let's say that I want, I don't know, 10 millimeter. So that means 5 this way, 5 that way. Okay. So parabolic, fine. Okay. Now, all right. So this is something new. We have never used this thing before. I've never used this guy. Okay. Add, remove, constraint. Add, remove, constraint. I never did that when immediately meshed it. So I want to add, remove, constraint, and I'm going to select this point. The point. Okay. I got the tab. Make sure you get this tab, the points tab. See that? Points tab. And then you go and select this point here that I created right there. That was point 2, this point. What this does is that it says, okay, when you generate the mesh, make sure this point is one of my nodes. Okay, and in fact, it allows me to apply forces and yeah, forces on this particular node. Ordinarily in CATIA, you cannot apply a force to a node. You have to apply it to a feature, which, but this turns that point basically into a feature of the element. And we say, okay. Okay, and now we measure. Notice that what it did is made sure that this is a node. Okay, now this is an ugly mesh, and I understand that, and you can work on this thing and get it to make it look better, etc. As a matter of fact, let's try to make it look better. Cancel that. Let's double click on this guy again. Let's go back here. Where's the mesh? Right there. Double click on this. Let's make this thing maybe uh, uh, let me do the following. Let's do quad only. Okay, how about checking quad only? Okay, that's fine. And then mesh it. Okay, this is better. Cannot do quad only, so we say fine. Let me exit this. Where is the exit? Right there. And try it again. Double click on this. I want to change the size. Let's make it. How about 4 centimeters? Okay. So let's make it 5. Mesh it. Ah, this looks a lot better. All right. My point is that this trick, it doesn't matter how ugly the shape of this mesh is. You need a trick to make sure that the point that you want to apply load at is actually a node. And I tried a few sizes. You notice that they get ugly meshes in this area. But if you don't do this, there's no way you can apply a force in the middle. Okay. All right. Good. So exit. All right. And we're done here. So let's go to generative structure analysis. Okay. And let's, if you want to see the mesh again, right click mesh visualization. It's nice, fine. Deactivate the mesh. All right. Now we're going to go and uh, apply our forces and things like that. Remember, we started with a static analysis. The problem that you want to do is not static analysis. Okay. All right, but that's the first step. So the first thing I'm going to do, remember, I hide my sketch, I hide my stacking so that I can pick the stuff on the edges. Okay, so first of all, these edges are all clamped. All these four are clamped. This one, and that one, and that one, and that one. They're all clamped. All right. And then I want to apply a force, a static force at this point, and I'm going to use. Let me see now. What is the number that I chose here? 40 Newton. Okay, 40 Newton. So concentrated force. See now, there's the concentrated force. It doesn't say concentrated, but anything that you want to apply to a point, an edge, a face is this. So that is the point, okay? And it's 40 downward, okay? Minus 40 Newton downward. You can see that it's down here. You can see this right there, right there. I'm gonna hide this rosette. It's right there, okay? Now, one of the things that I didn't do was probably to join this thing. I didn't flip the arrow when I joined this, and I don't want to do that right now because, and that's why this force ended up at the bottom, showing up in the bottom. Ordinarily, I go and I go to join, double click it, and flip it down so that I can see my my forces and pressure and things like that better. But I forgot to flip it down. Probably this is still probably the joint is pointing up, but it's okay. That's all right. Now, uh, yeah, don't forget to import the composite properties right there. So it's that support, and by ply, there's four of them, right? Stacking sequence right there, and we say okay. And symmetric because it's going to be symmetrically placed above and below that plane, and nothing exotic is going to happen. We're going to run it, it's going to work, and it's going to bend down. It's a simple static problem. We can check it out right there. You can see that average ISO, and you change the rendering, you can get nice colors and things that you want. Okay, good. Now the next step is getting the frequencies. So what we do is first of all, let me deactivate this. The next step is to go and insert a frequency case. And for the restraints, I'm going to use what's already there. I'm not going to make new restraints. I'm going to use what's already there. And I say reference, and you select it from the static case that we ran, the restraint right there. Okay, say okay. Nothing fancy. It's going to extract 10 frequencies by default. You can see that if you double click on this, the default is 10 frequencies. That's okay. We just leave it the way it is. And we're going to run it. Again, nothing exotic is going to happen. It's going to extract 10 frequencies, and we can plot the mode shape. Now, remember, this is one of the more expensive steps in doing the calculation that we're doing. Okay? But 10 frequencies is nothing. So, all right, so let's check it out. Click on the deflection, double click on it. Notice that there are 10 frequencies, 10 modes that we can look at. So that was the first mode, then these are the other modes, etc. Okay, cancel. We're back there, and we say okay. Good. Now, let me deactivate this. And then we're going to say insert. Now, this is the one that deals with time. I don't want this thing. I want this harmonic dynamic response. You click on it. Okay, it says frequency case. All right, I'm going to use the one that I just ran right there. We need these frequencies. And for load, is it new or is it reference? Well, it's load excitation. We're just going to say new. That's fine. Okay, double click on it. Double click on the load excitation. Notice that for the selected load, it's not a problem. I can go and select my force that I put in there. The only problem is it's also asking for the modulation. And I did not create a modulation. This is a constant force across all frequencies. So I can use white noise, okay? I don't have to create an Excel spreadsheet, basically amplitude of the force versus a frequency. I don't have to do that. It's a simple case right there. You see that? Modulation, white noise. That means same force for all frequencies. We say okay, and it's going to put it here in the tree right there. Okay. Now we're going to do what we were about to do, but didn't finish it. So load excitation. For the selected load, this is going to be that concentrated force that we applied right there. This was the force, remember? And for the modulation, we're going to select uh, the white noise right there. Okay. Now this we're going to keep the scale factor of 1. In other words, don't worry about it. Just use the 40 newtons that I gave you. But if that was 400 newton, then I would have to do a 10 here. I can do a 10 here. Okay. I can either change it from the load or I can change it from the selected factor. You say okay. All right. Now let me also remind you that by default, there is a damping. If you double click on the damping and you click on the range, by default, all modes, all frequencies, or all the modes for the frequencies are uh, given a 1% damping ratio. So if I don't want any damping, I say 0 here, and I say okay, and close this thing, and we are pretty much done. So let's go ahead and run it first. This is going to be model superposition, very quick. And let's go and get the information that you want. So look at uh, oh yeah, the only thing that I forgot to do was the range of frequencies. I forgot to do that. So let's do that here, right here, harmonic dynamic response, double click on it. So we want to do things from, let's say, yeah, let me see what range to 200 hertz to 1000 hertz. So do the calculation from 200 hertz to 1000 hertz. And let's put 1,000, or no, 1,000 steps there. It's not 500 steps. Okay. All right, that's good. And now we're gonna right click, put the cursor here, right click, create a 2D display, say finish, and it says, okay, go pick your node, and what is it that you want to plot? Well, first of all, I want to plot the amplitude of the displacement in the Z direction. Okay, so minimize this, and go and select that node. Now, that node was the center node where I applied the force, right? So if I can't see it, the best way is to go and say, all right, show me. I can do it from the I can do it from, say, show the mesh, show the part, and now go and select this node. You see that? Because there is a node sitting right there. Right there. I want this. Okay. Now, if this is blocked, oh, right there. See that? Which is node 5. And we say okay, add. Okay. And we say close. We're okay. So let's look at our plot. There we are. So what this thing is, well, first of all, this unit is in meters. Okay. So let's change this thing back to the units that we want. So put the cursor there, right click, put the cursor in the white area right there, right click options. Don't give it to me in terms of meters, give it to me in terms of unit that I want, which I believe was, I don't know, I thought it was millimeter or something, but it doesn't look like, oh yeah, centimeter. Okay, very good. Okay, now, so what this is telling you is that when this force is being applied at different frequencies, okay, the the amplitude of the deflection at that location, center location, is given by these numbers. Now, if you see here, there's no damping, and we have a frequency. We have some frequencies which were actually natural frequencies, which are less than 200. That's why I had the frequency down here on the left. That's why I missed it. So let's go ahead and clean this up. Let's actually go ahead and go back to this. Harmonic dynamic response. Let's not do it from 200. Let's do it from 0 hertz to 1,000 hertz. We say okay, and now look at the plot. get it from here. Okay, it shows you even the lower frequencies. So let me remind you that one of our natural frequencies, the first one was around 180, 90 or something like that. That's why there's a resonance here. When the frequency of the applied load, which is down here, is equal to this first natural frequency, you get resonance. Here are the other natural frequencies, okay? And in fact, we can double check that. If you go here, I should have, let's go here. Let's check our frequencies because I can't remember what they were. Uh, see, 180, and then it goes to, and the next one is 300 and 400, etc. So for each one of those, in principle, if you have done a fine enough resolution of that table that we filled, you're going to get a peak. So where is this? Right there. Okay. Now, if you see if you don't see the peaks here, means that it was not fine enough. We probably missed it. But let's add some damping there. Let's add some damping. So where's the analysis? Yeah. So we go here to damping. Let's add some damping. The good old 1%. Maybe 1%. Okay. We say okay. We don't have to run this thing. All we do is you double click on this, and it shows you that the peak doesn't go all the way to infinity, but it drops down. Okay. So we found the amplitude of the displacement of that center node as a function of frequency. Okay, so if this was a fan hypothetically and it was going at a certain RPM, it's operating frequency in hertz, and then you go here and you find out what is the amplitude of the displacement at that center point under this fan, and there we are. So this is the concept of frequency response or harmonic. What was the name of this thing that they call harmonic dynamic response, etc. Okay. So in the next video, what I'm going to do is I'm going to redo this problem, except that the the uh, the amplitude of the force depends on the frequency. In this case, it was constant. It was that 40 Newton that I applied, okay? But it can vary. And for example, that business of centrifugal force of an unbalanced rotating machine, the magnitude of that force is mr omega squared, okay? Not a constant. It's a function, it's a parabolic function of omega. All right, folks, good luck.